Okay, alright. Okay, good morning, students. Mic check. Is the sound clear? Please raise your hand. Okay, thank you. Okay, so today I think that we no need until 12 o'clock. Okay, I think I can finish earlier. So we continue from where we stopped yesterday. Okay, so yesterday we already done for the drawing, okay, the formations of the image by the concave and the convex lenses. Okay, we learn how to uh, complete the ray diagrams, right? Okay, so as I told you, when you study, you see that the table 6.6 is told you there's a three different rays can be used to form the image by the lenses. But when later on, when referring to the table 6.7, or you recall back what we learned yesterday, we only need to use two out of the three rays. We can form the image already, right? So we no need to use up the third rays, right? So anyway, because of the drawing when it came out in exam, so due to the limitations of the marks can be given by the each sub question, so even you draw the third ray is also useless because there's no any extra marks will be given. Okay, because the requires of the drawing is as long as you're able to show that the intersections for the at least any two rays, okay, to form the image, then you can get the full marks already. Right. Okay, and then just have to remember when you draw the rays, you have must include the errors. Okay, must include the errors. Where is the ray pass through? Where they will meet. Okay, and for the dotted line, okay, or the solid line, dotted line, especially for the showing that is a virtual ray to form the virtual image. So that one is not necessary. Okay, even you referring to the textbook, you see when there is a virtual ray to forming the virtual image, they all use a dotted line, right? So as you can see here, this is part of the virtual ray, and then this is also the part of the virtual image with the virtual ray. Okay, so all this using the dotted line included the convex lens also same. Okay, they're using the dotted line here. So, but the exam, okay, we don't really care whether you use dotted lines or the solid line, right? It doesn't matter. Okay, as long as you know how to study the characteristic of the image, and then you know how to form the image. Okay, so the next one, from the image that we draw, we notice that the size of the image is changing. Right, size of image is changing, depends on the object distance. So due to that, we have the ones equations for these calculations on the magnifications of the image. These magnifications, okay, we call it linear magnifications based on the single lens, and it's not necessarily only count how much the image will be magnified, even they call it magnifications. But actually, this magnification is one of the factor to knowing that whether the image form is become bigger, same size, or smaller. So the calculation result, when you get the linear magnification, which is a symbol m less than 1, so it means that the image will become smaller, so that you will get the diminished image. When equal to 1, it means that based on the calculation, v over u, image over object. When the image over object, you get the 1, so it means that they are same size. So when the image over object, you get bigger than 1, so image is magnified. It means that the image is bigger. Okay, so for this equation, actually it's just a mathematics. Okay, when referring to this diagram, it's just a mathematical calculations for the triangle, right? As you study from the triangle, okay, when you see here this diagram, as you study in the triangle relationship, so you can see here there is one triangle here. I use okay, purple colors line. So here you see there's one triangle. and there is another one triangle. Right, so all together like this also can. So from here you can see that they are sharing the same gradients, right? They are sharing the same gradients. So as you know for the mathematics, okay, when there's a triangle sharing the same gradients, something like this, so it means you have a b actually equal a b. So it's just like the way we calculate the gradients. So when we have the a over b, it should be equal to the small a over this b, based on the understanding about the gradients, right? A over b over equal to a over b. So that's why based on here, when you have this height is the object height, which is a HO, and then this height actually is the image height. Then we have this distance is object distance with the symbol U, and then this distance as given here is the image distance. That's why we will have the image. We will have this equation, magnification equations, linear magnifications, which is have image height over the object height. It will equal to the image distance over the object distance. This is how we get these equations. Right? It's just based on magnetic. You need to understand this because sometimes the question will give you based on diagram. If I know wrong that day, I think the triad I give the one essay question for this, right? Similar like this one. Okay. So once you understand about the triangle concept, so due to the ligand that you draw, it shouldn't have a problems lah. Okay. So this is about these magnifications equations. Okay. And then for the only practice 6.3 here, okay, what are the characteristics of the image shown in the figure 6.35? So from here you can see this is the image that you see inside the lens, convex lens. And then behind here, this is the object. Here's the object. Okay. And then this is image. Okay. So from here we can see image is magnified. All right. So this is one of the characteristics. Image is magnified. So when you mention the characteristic, we have the three different characteristics have to be mentioned. First one is about the size. First one about the size. Size, it can be diminished, same size, or magnified. Okay. So if you don't want to use this term, you can just use a simple term, smaller, same size, bigger, also can. Yeah, but officially when we describe about the characteristic of the image, we will use terms diminished, magnified, or same size. Okay. But come to the exam, if you're having problems to write diminished or magnified, because I noticed that especially the Form 4 girls, okay, quite numbers of students, your English no really, the writing is not really good, the grammar, and then when you give the answer, a lot of the errors in spelling, right? Okay, like today, there's one paper, the question asking about the design of the solar cooker. If you still remember the Form 4 girls, the design of the solar cooker, about the size of the disc, okay, the parabolic disc. Okay, so I think that the girl is not really focused when you answer the question paper. When she when she respond the questions, it's about the disc, the parabolic disc or the solar cooker, right? So, but I don't know why she write there fish, FISH. DISH become FISH. How are you going to give you a marks? Okay, so first one is about the size. Okay, when you mention the characteristic, first one about the size. Second is about the image form is virtuous or upright. Okay, it's about the positions, about the how to say that, whether the image it can be projected or cannot project on the screen. All right, so this is about the real or virtual. Okay, this is second. You have to mention real or virtual. So it means that it's either real or either virtual. It cannot be appear at the same time. Some students, when they ask about characteristic of the image, the student just write everything that she know. It happened before. It just list out all. Okay, real, virtual, diminished, magnify, same sign. Okay, upright, inverted. You list everything out doesn't mean that you can get full marks. It's just like you memorize the textbook from the page 1 until last page. And then after that, within the 2.5 hours, you write the whole books out again. You will still get 0 marks. Right? So when you answer, you must know. Okay. And others than the virtual, either it's virtual or real, then the next one you have to answer whether the image is upright or inverted. Upright or inverted. Okay. Yesterday, based on the discussion, I already told you there is a padding that you always have to know when you have the object is upright. Okay, upright always virtual. Upright always virtual. Okay, and inverted always real, or real always inverted. Okay, real always inverted, virtual is always upright. Okay, so these two padding is confirmed when you have the single lens. Right. So why I keep mentioning about the single lens, because later on when we learn about the optical instruments, so the optical instrument usually it will be formed by the two lenses. When the two lenses, the final image compared to the objects, the final image characteristic will be different. Right. So that we discuss that one. Okay. So this padding. So means that if you during the exam you're really not sure whether what is the characteristic of the image from, you don't really understand about questions. So when the question asks about characteristic and then you see the marks is 2 marks or above, you can try your luck. Either you all in, or either you try your luck at least get 1 marks. All in means that these two padding, you give either one. All in. So either you get 0 marks or either you get full marks. If you want to try your luck, at least get 1 marks. So it means that you mix the padding. So virtual mixed with the inverted. Virtual mixed with inverted, at least you can get 1 marks. Or the upright mixed with the real, at least you can get 1 marks. This is chances. All right. Okay. So depends on how you think lah. Okay. Either you want to all in, or either you just want to get 1 marks. Okay. So for these questions, okay, obviously there is a magnified, one of the characteristic image, because image bigger, and then the next one you see that is the 15:10 also is upright, so the image is upright because it's not inverted. Okay, and then once it's upright, it means it must be virtual. All right, so that is how we know about the characteristic of this image, and then draw the diagram to show how the image in the figure is formed. All right, in the figure is formed. So you remember when you want to draw this diagram for a convex lens. Okay, yesterday I told you already. When you have the lens here, so this is your focus. So remember, focus is the critical border, because once when the object located here, when the object located more than focus, right? So your object will be real. Once object located more than focus, it will be real. Okay. When on the other side here, which is objects located less than f, so your image will be virtual. All right. When the object located at f, so you have no image at infinity. All right. So in this case, you already know that the image is virtual. So it means that when you ask you to draw the ray diagram, show how the image is in the figure is formed, you must show the object located less than f. So you must show the object located less than f. Then after that, you continue complete the ray diagram as we learned yesterday. All right, so you will get the full marks easier. All right. Suggest a suitable position to place the object to produce an inverted image. So inverted image is what? Inverted image must be real. Real always inverted. Real always inverted. So what is a suitable position? Object located more than f. Object distance located more than focus length. Then the image will be inverted. All right. So that's all for this 6.3. Okay, so actually what we learned about the characteristic image, okay, for the drawing like game yesterday, right? We do have the options by using the lens formula or the lens equations to knowing about the characteristic of image without drawing, okay, without drawing, okay, by the using this formula, okay. And actually before this, before the KSSM textbook, right, in the old syllabus, there is no any books, included the reference book, discuss about using these equations or using this lens formula to determine characteristic of image. There is no any books, right? But in my module, already used more than 10 years, I already told the student we can use this formula to determine the characteristic of the image. And actually, I have write a paper for the action research, which is the teacher actually require every year do the one action research. Okay, so we want to implement some methods to helping the student improve understanding in their learning for the subjects. So by right, the teachers every year have to do it is very small method. Okay, so this is one of the method that I already implement, and then I write the paper to join the one action research competitions. So and somehow in my module I use it more than 10 years. I share with a lot of teachers in Malaysia. So now they officially put it into the textbook. So same as I told you before. There are many content, the way how to edit, the understanding of knowledge in the textbook. Actually, I will say that it's very, very similar to my module, right? But I don't know how they get it, where they get it. Okay, so okay, they just not respect to the copyright. Okay, at least they have to notice me about that. They're going to use it in the textbook. But anyway, the knowledge is not come from me, right? I just sharing the methods on you. Okay, so these equations, this then formula, all right. So as given here, okay, this one the experiment 6.3. Actually, we use this experiment to determine the focus length. All right. Okay, because by given these equations, the objective actually is to use the object distance and the image distance, object distance and image distance to get determines the focus length. Okay, to determine the focus length. So through this uh, experiment. Okay, so this experiment you can see. All right, so we have the convex lens here, and then we have the object. So there's a bulb so that they can light pass through the object. Okay, and then pass through the convex lens, so it will form the image on the screen. So basically, these experiments, all we did is for the real image. If for the real image, so it means that later on when we see the image appear on the screen here, will be upside down, will be like this. Okay, because this is objects. So when light pass through, so we're forming the image upside down. Okay, and then the size doesn't matter. The way how we do this experiment is we need to adjust. We need to adjust the convex lens by changing the object distance, right? So with this one basically is fixed. So when we adjust objects, the lens forwards, so it will make the object distance shorter. Okay. So after that, after we adjust the lens already, after adjust lens already by changing the object distance, then we have to adjust the screen behind here, backward and forward. Okay, by changing the image distance. Why we need to adjust the screen after we fix the object distance that we need? Okay, because we need to know where is the position can form the sharp image. Okay, so this is the one that yesterday I didn't discuss. So based on this ligand, okay, example for this ligand. Okay, so from the ligand we see here the image is forming here. The image is forming here. So it means that when we have the screen here, just like the experiment they show on the next chapter. So here is there is a holding the lens. Okay, so we have the objects putting here. Yes, this is the object. All right, they all arranged in parallel line, right? So yeah. Okay, and this is our bulb here, our red box. Okay, so there's a light pass through. Okay, so we already adjust the position of the lens, so we have this object distance. Right, you have this object distance, and then after that we need to adjust the screen here so that we can get the image distance. Okay, so we adjust the screen. When we adjust the screen, put it here, so we're able to see that it's a sharp image. Okay, but if let's say the screen is not at this position, let's say we're putting the screen here. Let's say putting the screen here, right? So it means that the image forming is like this here, at here. So we will see the image, but the image is blurred, not the sharp image. The image will be blurred. All right, means that the light is not focused. The light is not focused to one point to see the sharp image. It's just like we're adjusting the screen and the projector in the school, right? So sometimes we fix on the projector manually. Sometimes we fix the projector manually. Okay, so that's why we always have to adjust the focus so that the sharp image can be formed on the screen. Right? Okay, it doesn't mean that when the screen is not on the position, there will be no image form. Image will be still formed. Only the image is blurred. You can't see. Right? So means that when this one is a parallel ray, totally you only will see the light. You only will see the light when you put the screen here. You see there is a light. Okay, but you can't see image at all. It's totally blurred because the light is not focusing. Right? So you just see there is a blindness light appear on the screen. But you can't differentiate this a tree, this is a table, so what when the image, because you can't see the image, right? It's totally blurred, right? Okay, so that's why this experiment we need to adjust, right? Adjust the position of the screen until we can see the sharp image. Then after that we stop, then we measure the length. The length will show that is the image distance. Remember, all the measuring is measure from the positions of the lens. Right? For the lens toward the object is the object distance. For the lens toward the image is the image distance. Okay, so this is how we do this experiment. So and then later on when we get the results already, we need to calculate 1 over u and 1 over v. Okay, we need to calculate 1 over u, 1 over v. So same as similar to our experiment that day, the practical exam. When we do the calculations, so we can't say this is a manipulator's whatever. We cannot say this is a responding whatever. No more. Because our manipulator whatever actually is here. This is our manipulator's whatever. This is our responding whatever. And both of this is calculation secondary data. Right? So you cannot call it as manipulator or responding. No. All right. Okay, so please do no misunderstanding. It must be always plot the graph V against U, must 1 over V against 1 over U. It depends on the need. So anyway, this graph we're going to plot is a 1 over V against 1 over U. Right. So from the graph itself, we need to ask to determine the gradients. So you see here, when you plot the graph 1 over V against 1 over u. So from here, when we calculate the gradients, so okay, I'm not sure whether there is directly proportional or not. If you want to know about whether there's directly proportional or not, so you need to see the equations. So anyway, so let's say there is a directly proportional. Later we discuss whether this directly proportional or not. Okay, so from here, the question asks us to determine the gradients m. All right. So gradients m is what? It will be 1 over v against over 1 over u. So 1 over v over 1 over u. So it means it's a 1 over v multiply u over 1. All right. So it means it's a u over v. So u over v is a gradient. And then this gradient can be presented anything. Right. So u over v presented anything. So this one can actually okay, when you go to equation 1 over f equal to 1 over u plus 1 over v. So in this case, you see, in this case, is that possible we get the u over v? Right. So anyway, how we delete these equations into our graph? Our graph is 1 over v against 1 over u. So now we see here. If we have y-x here for the graph like this, directly proportional, let's say, okay, so gradients m means that according to this graph, we have the equation y equal to mx. So means when we have the 1 over v against 1 over u, then the gradient, so we should have 1 over v equal to the gradients multiply 1 over u. Okay, this is one. Okay, and the next one, when you have the 1 over f equal to 1 over u plus 1 over v. All right, so now referring to this graph, this is similar like here we have the y, which is this one actually is a y-axis. This one is the x-axis. So this is the x. Right. So how we're going to rearrange these equations, make it like the general equation. All right. So we do rearrange it, we have the y equal to 1 over f minus x. Right? So then the y will equal to the negative x plus 1 over f. So according to this, means that you have the 1 over v equal to negative 1 over u plus 1 over f. So compared to the general equations, y equal to mx plus c means our intercept for the graph 1 over v against 1 over 1 over v against 1 over u, it should have the negative gradients. It should have the negative gradients, right? Negative gradients, and intercept will be the 1 over f. So it should have the negative gradients, right? So negative gradient with the intercept here is equal to 1 over f. And the intercept should be positive, only the gradient is negative. Right, so it means that the graph it should be like this. So from here, okay, so it's possible see whether we can do these experiments or not. So it means that according to that, we should get the negative gradients according to the length equations. According to this length equation, the result we should get the negative gradients. Okay, so this is about this experiment. But anyway, from here you can see there is no asking about it's not asking about the gradient presented what. All right, so because it's not really using the lens formula and graph plotted determine the focus length for the lens in this experiment. So it means that it's not asking you about the gradients it presented what, but it's asked you to use a graph plot by comparing by the lens formula as I showed you just now, how we determine focal length? So by right, you can get the focal length by 1 over f equal to intercept of the graph. So later on, to get the f, you have to use 1 over intercept of graph to get the focus length. Right? So it should be in that way. All right. So this is about the formula. We use lens formula and also the experiment how we determine the focus length. Okay. And then the next one, okay, the solving problem involving the lentils lens formula. As I told you from the beginning, we can use the equations to determine the characteristic of the image form. All right. So remember, we have the two type of lens. Before we learn how to use the equation to determine the characteristic of the image, we need to know something first. First one, we have the two different lenses, which is we have the convex lens, right? We have the concave lens. Okay. So once you have a convex lens, remember yesterday we learned already. Convex lens we have the real image. Convex lens we have the real focus. Okay, convex lens we have the real focus, so that's why the f is positive. Okay, remember when you apply these lens equations, positive means is for the real, negative is for virtual. So concave lens we have the virtual focus, so that's why f must always negative. F must always negative. Same also, once you get the V result, which is image distance result, when you get a positive, it's showing there is a real image. When the result is negative, so it's showing there's a virtual image. So once you know there's a real image, means you must know real always inverted. When you get the virtual image, that means you should know virtual always upright. Right? Virtual always upright. So once you know the positive V or negative V, automatically you will get to know about the two characteristics of the image already. Either they are real or virtual. Once you know the real must be inverted. Virtual must be upright. All right? So at least you know the tools already. And the last one, whether the size is the same size, bigger or diminish, magnify or diminish, we have to look at the V value, the V magnitude, right? Compared to the U, compared to object distance, right? So now we practice with the example questions in the diagram here. All right, so like this case, so just an example here. Okay, assuming that we don't know about the image, we only know the objects. So objects located here. It tells you about this information. Right? So we don't need to look at the diagrams. Just look at this one. Okay, objects O between F and 2F. All right, so this is for convex lens. When for the convex, okay, convex at least we know the F is positive. F is positive because convex we have the real focus. Okay, and then the O is between object is between F and 2F. So when we want to do the calculations, we try to get any value. Example, we try, okay, assume, let's say F equal to 10 centimeter. Just put any value. Just put any value. So now O is between F and 2F. So it means that it's between 10 and 20. So you just get any number between 10 and 20 as an object distance. So in that case, we can use a U, let's say in between, so we take the center lah. So we take the middle, so 15. Right, so 15 will be between F and 2F. All right, so now we do the calculations. 1 over 10, it will equal to 1 over 15 plus 1 over V. So 1 over V will equal to 1 over 10 minus 1 over 15. Right, so just use your calculator, right? I don't have a calculator here, so I do it manually. So I put it as 30 here, This one will be 3 minus 2. All right. So it will be 1 over 30. Okay. So it means that I will get the V is equal to 30. All right. V equal to 30. All right. 30 centimeter. So now this is a V result. So from the V result here, we know that it's a positive V. Positive V. So it means positive is for the rear. Positive for the rear image. Okay. When it's rear, rear must be inverted. Here must be inverted. All right, so at least we know the tools already. And then the last one is the size. So now you see the V is 30. V is 30, but the U is how much? U only 15. So it means that the V is more than U. So now this is magnified. Right? So now when you compare, so see rear, inverted, magnified. So this is how we do the calculations. Without drawing, we're able to know all the characteristics of the image. Okay. And then we can apply with this diagram also for the virtual image. Okay. So now, like the same like just now. Okay. This is a convex lens. So F is positive. Okay. The U less than F. So let's say we fix the F. Now we try to fix the F as 20. We change. So let's say F is 20. So the U must less than F. So U less than F. So let's say we put 10. As long as it's less than F. Right. So now we want to know about the V. Okay, so 1 over 20. 1 over 20. 1 over 20, it must equal to 1 over 10 plus 1 over V. So 1 over V will equal to 1 over 20 minus 1 over 10. That's equal to 1 minus 2. So it equal to negative 1 over 20. So the V will equal to negative 20 centimeter. All right. So now we get the V equal negative. So this is our V. V is negative. Negative means there is a virtual. So virtual must be upright. Virtual must be upright. Okay. So now about the size. So remember, when we want to compare the size, okay, we only compare the magnitude, which is 20. We compare 20 with 10. Not the negative 20. We compare 20 and the 10. So now 20 is more than 10, then the image will be magnified. Okay, image is magnified. So we don't take negative 20 because negative is just only let us know whether there is real or virtual image. So basically, image distance, you can consider it as a vector quantity. Even we call it distance, right? It's just a name. But image distance actually is a vector quantity because positive negative, it just only lets us know about the position. Position either is the same on the same side with the object or on the opposite side of the object. Right? Means that to let us know whether it's a real or virtual. All right. So the conclusion here, the image is a virtual, upright, magnified. So we look at the result here, virtual, upright, magnified. Okay. So this is how we use the lens equation to know about the all the characteristics of the image. Okay. And the explanation in the textbook is not really complete about the how we use the equations to get the characteristic of the image because it's included by using the linear magnification to know about the size of the image. Right? After you get to know about the V, then after that we use the magnifications. Right? So just only you see here, it doesn't have any explanation in detail. This one you see the -6, but when we substitute into the linear magnifications to compare whether the size bigger or smaller, so you see it's only substitute 6. There is not included negative. Not included negative, right? So You have to remember about this, because the negative in cell just only that you know that is the negative in cell here is just only that you know that is virtual or real. Right? Negative is a virtual. Okay. So that's all about the 6.4. Okay. So it's applications of the equations. All right. So is this okay? If yes, please raise your hand. Okay, so down your hand. For the Form 5 student, I hope you still remember that day the paper one in our trial, there's a one questions I designed uh, to related with the dense equation with the graph. So the question actually is quite challenging. I hope that you recall back about that, how we apply the length equations to relate with the graph, because based on this equation we can change a lot to make it relate with the graph, right? So there are many possibilities we can design the question, right? So once you have a similar questions like that, what you can do is you try to make the graph understanding on the general equation on the graph, try to compare with the length equation as what I did just now. Okay, like this one, what I did just now for you is one of the idea to let you know how we use the graph to relate with the equations to know about the information that we can get. Right. So this one must based on the some experience lah. Okay. So that's why one of the reason why the chapter one in Form 4 actually they discuss all the graph relationship, right? Because all the equation in our physics concept or the physics law or theory, when we have the equations, or we will relate with the graph. That's why basically all our experiments we need to plot graph to see the relationship between the quantities, because all the relationship it can be related to the equations, right? So now the next one, optical instruments. Okay, optical instruments. So I'm not going to go through detail, right? So basically, you need to read by yourself. All these informations to let you know the occupations, okay, that related to the lenses for the optical instruments in our career, right? So you see, it just tell you I'm the gemologist, okay, I'm the astronomer, I am the ophthalmologist, okay, I am the microbiologist, I am the geologist, okay. So all these occupations that will be used optical instruments in their work. All right. So basically, all these instruments, optical instrument, it can be divided into the three main instrument, which is a magnifying glass. Magnifying glass is just only the single convex lens, right? If you want to talk about instrument, basically it's either become the microscope or either become the telescope. Okay, by using the two different lenses. Okay, so two lenses combined, okay, become the microscope and telescope. So that's why you see the textbook, it will be main focus on the designing and building a compound microscope and the telescope using the convex lens. The first thing you have to understand, it must be used of the convex lenses, not the concave, because concave is never magnify the image. Concave lens, concave lens is only will make the image smaller, diminish. Right? This is only one characteristic by the concave lens. So remember here, this one, only one characteristic, which is virtual upright diminish, virtual upright diminish. Always smaller. When always smaller, actually our instruments in our applications not really useful, and they only on the certain specific use, they only will use a concave lens. If not, basically we want to amplify the image so that we can see the detail, amplify the image so they can see the details on the objects. Remember, what we amplify or what we magnify, what we make it bigger is the image, It's the image, girls. It's an image, not the object. Never mention in exam it can magnify object. Please, Alright, I repeat many times already. Never mention it can be magnified object. Object is just fixed already. You can't magnify object unless it's only happened in the cartoons, in movie, right? Like the Ant-Man, you can magnify Ant-Man. But in reality, we can't magnify. We only can magnify through the image forming, right? So you see the Doraemon have the special torchlight, okay? When it shine on the object, object can be magnified. So that is only the tools given by the Doraemon, right? In our daily life, we have no Doraemon. In our daily life, we have no Ant-Man, right? So in our daily life, we don't have the Harry Potter. We don't have the dark magics to make anything become bigger. No, we only can use a lens to magnify the image, right? Please remember, Hopefully next year, current Form 4, next year, our exam, everything, I don't have the answer that show me magnified objects, okay? But I think the possibility to get the answers still there, okay? Because the number of students attend the class is really less, and mostly actually is a Form 5, okay? So we're talking about this microscope and telescope. All right, you see here, it's told you everything detail. Microscope, compound microscope here, everything details here, and then there's a ligand. And we have the telescope, everything details here, and there's a ligand. So all this is for you to read. All this is for you to read. For me, I'm not going to go through one by one like this. I made the conclusions for you how to understand it. Because if you read like this one by one, finish microscope already and then go to telescope, I told you, you will still don't know what it's talking about. All right. So I'm going to combine it. Today you understand how to make the difference between these two. Okay. So first, either telescope or either microscope, both we're going to use two lenses. Both we're going to use two lenses. Okay, when you arrange the two lenses, okay, when you arrange the two lenses, the one thing is very important for us is for the arrangements of these lenses. The arrangement of these two lenses is we must know the length between the lenses. The length between the lenses. Right. So this is the first to differentiate the arrangements on the telescope and microscope. First is about the length between the lenses. Okay. For this length between the lenses, we're going to compare. Compare with what? Compare to the focus length of the objective lens plus focus length of the eyepiece lens. So what is the objective lens? What's the eyepiece lens? Okay. So for the either telescope or microscope, we have the one objective lens, which is facing to the objects. We call it objective lens. Another one, the eyepiece lens, is facing to the positions of the eyes. So we look at the design here. Okay. So for the microscope, so we put the eyes here. We put our eyes here. So it means that the lens here, this is the eyepiece lens. And then we have another lens here, this one, the lens here. This lens is facing to the objects. Facing to the object, so this is the objective lens. Okay, this one's the objective lens. Right? Objective lens, this is the eyepiece lens. Okay. So same with this one. We have the lens here. It's facing to the object, so this is the objective lens. And here, we're putting the eyes here, so this is the eyepiece lens. Right? So there is the understanding about these two limbs of the lens here. Okay. So the length between the lenses, we're going to compare with the FO plus FE. So when we compare to the FO plus FE, we have the three different results. Either this length must be more than FO plus FE, or either it must be equal to FO plus FE, or either it will be less than FO plus FE. So we have the three different adjustment. All right? Either it's more than FO plus FE, either it's equal, or either it's less. So now we see how it look like for more, equal, and less. Okay. Okay, so we have the two lenses here. Okay, so let's say this is our on the left hand side here also objective lens. All right, so our eyes is here. So it means that the yellow color is objective is eyepiece lens. All right, white color is objective lens. So for those you make your own notes, you can do it labeling like this. Okay, so now for the now we only focus on the arrangements, the length between the lenses. Okay, so we still haven't discussed yet FO bigger or FE bigger. No, we haven't discussed that part yet. We only focus on the arrangement, the length between the lenses. Okay, so when we have the objective lens here, so this is let's say we have the length more than FO plus FE. Okay, so how is it should be look like? Okay, so here is the objective lens, the white color on the left. So we should have the FO here. This is the FO. Okay, so and then the FE should be here. FE. Okay, so that our this will be our FO. Okay, and this is our FE. So our length L, it will be more. L will be more than FO plus FE. Right? So means that if this happen, FO and FE will have the gap in between. So that make the total length between the lenses is a FO more than FO plus FE. This is happen. Right? Okay. So the next one, if we have the length between the lenses is equal FO plus FE. So how it look like? Now it's equal to FO plus FE. So it means our FO and FE shading on the same position. So here to here is FE. Focus length of the eyepiece lens. And here to here will be focus length of the objective lens, FO. So since the length is equal, the length between the lenses equal FO plus FE, so that's why FO and FE, they were shading on the same point, so that their total is equal. Right, so this very special, they will be shading on the same positions, FO equal to FE. Okay, FO no equal to FE. FO located same as a FE located, so that their total is equal. Okay, so now the next one is less. The length between the lenses is less than FO plus FE. So once less means that they're going to exchange. So it means that our FO will be on this side, FE will be on the other side. So means they will overlap, they will exchange the position. So here is our FO, and here is our FE. So they exchange. Then to make the length be changed, it will be less than the total. So the length is less than FO plus FE. Okay. So regarding this arrangement length compared to the sum of the FO plus FE, either more, equal, or less, can you understand or not? If yes, please raise your hand. Okay, so this is just a mathematical lah, right? Mathematical. Okay, so now based on these three arrangements, how we know which one is for the design of the microscope, which one design of the telescope. Okay, so now back to this one. Okay. So the length between the lenses. Okay, so this one, why it focus on the other side? Because actually inside they have the prism. Inside they have the prism deflect the light. Okay, inside there's a prism deflect the light so that we can see on the positions like this. Okay, so but when we draw the game, we're assuming there's a lens is here, right? So that's why you have the distance like this. Okay, so this is a length between the lenses, right? Objective lens and eyepiece lens. And this one also same. There's a mirror and the prism inside is to reflect the light. Okay, so that's why in the different angle, right? But when we draw for understanding the design, so we're assuming there is a straight line. So by right, this is the length. So this is the length. Okay. So based on your understanding, and I know that most of you have seen about microscope, okay, but you don't really have the chance to use telescope. I don't know, right? So anyway, that is the diagram that you know that which one's a microscope and telescope, right? Okay. So now I want to know in these two instruments, which one the length can be adjusted? Which one the length can adjusted? Which means that we can change the length longer, shorter. Which one is fixed? So I want to know which one can be adjusted. Is the telescope or microscope? Please give me some response. Which one the length between the lenses can adjust? Is adjustable. The length between the lenses is adjustable. Telescope or microscope? Adjustable. Is a microscope or telescope? Engineering, you said the microscope. How about the others? This is all agree. Microscope, the length between the lenses is adjusted. I'm talking about the length between the lenses. I'm not talking about whether we can change the lens or not. Have you seen the pilot's movie? Like the example, the famous movie for the pilots of the calibrants. You see the pilots, they always like to use the telescope, right, to see the far objects. So Vinisa also said microscope. The length between the lenses is adjustable. Okay. So the others, not really sure, still thinking, why so many choose a microscope? Only 3 choose microscope. Okay. So maybe I should create a poll to let you choose. Okay. So wasting my time to ask your response. Okay. So girls, the adjustable length between the lenses is not the microscope. It's the telescope. Okay. So here, that is your lens. Eyepiece lens. Okay. Then here, objective lens. Objective lens, eyepiece lens. Okay. So in reality, all right, or the concept is the length between the lenses, the length between the lenses for the microscope actually is not adjustable. It's not adjustable. It's fixed. What you change is what? What you adjust is what? You are changing the different power. You have the three different objective lens. Normally the design. Because these 3 different objective lens is the different power. So when you adjust, actually it's still fixed. You see all these 3. Later on, when you go back to school, you can have a look. Right? Actually, these 3. Right? So it's the same, and then the lens located at the lower part here. So when you change, actually you still fix the length. So I know that you think you're talking about the adjustable is what you can. What happened? So you can adjust what? You can adjust this. You can adjust this up and down. It means that you adjust the whole part here. You make this whole part, okay, which is the arms here. With the arms here, with this arm here, you can make it up or down. But you are not changing. You are not changing. You are not changing the length between the lenses. You are not changing the length between the lenses. You only adjust this arm by the turning on this one. You only adjust it up or down. So you move the whole part here up or down. Because of what? You are changing the object distance. The object is on the platform here. You are changing the object distance so that you can see the clearer image. You need to change the object distance so that the image form on your retina will be clear. Right? So this is just like the experiment that we did before. When we change the object distance, we need to change the screen. But now when I put on the eyepiece lens, so your screen on your retina is already fixed the position. So when you have the different object distance of by the use of different power, so you need to adjust suitable object distance so that your sharp image can be formed on your retina inside your eyeball. Right? So that's why we change the whole arm. We are not changing the lens between the lenses. The only one can be changed is the telescope. Telescope is that's why you see always there's a 2 different arm. Sometimes there's a 3 different arms. Because of what? Is adjustable. Right? It's just like you see the pilots or the Caribbeans, right? So usually they have the short one keep inside the pocket. After that, okay, when they use it, when they use it, so they will pull until really long because they can pull it out. So once they pull it out, means that the lenses distance is changing. right? So the telescope, the length between the lenses is changeable, but the microscope is fixed, right? So means telescope we have the two possibility. We have the two possibility for the length between the lenses. Microscope only one is fixed. So why I said that the telescope when we changeable, why is only two possibility? Because when we pull the telescope, so let's say there's a telescope. So here is the eyepiece lens, then there is the objective lens, right? So we have the one we pull until the maximum. When the length pull until the max, right? Or either we pull it back, make it shorter. So there's a two possibility for the telescope. Either we pull until the max, or either the length is less than the max. So that's why we have the two possibility. But the microscope is only one. Okay. So okay or not? Can you understand? If yes, please raise your hand. All right. So give me a minute, sir. I'm going to settle the case upstairs. Okay. So and then at the same time, you try for those still a little bit confusing. Try to figure out what I told you just now about the length between the lenses. All right. Give me a minute. Later, come back. All right. So I come back already. Okay. So now we continue. Okay. So when the moment this telescope we pull until the max, right? So this maximum length actually we have a special name for it. When we pull until the end, we have a special name for it. We call it this one. We call it normal adjustment. Normal adjustment. Okay, which is given here. Normal adjustment is what? Normal adjustment is here. Normal adjustment for the telescope means that the length, right, is equal to FO plus FE. This is very important. Normal adjustment for telescope, right? adjust the distance between the objective lens and eyepiece lens is equal to the FO plus FE. So means for the max, when we pull the telescope until the max, so this max is the moment we have to equal to FO plus FE. So after that, when we pull it back, shorter. So when we pull it back shorter, so it must be have the length less than FO plus FE. Just like that. So there's only two possibilities for telescope. Either it make it to the max is equal, and this one we call it normal adjustment. Remember the name? We call it normal adjustment. All right, normal adjustment. Okay. After that, when we make it shorter, because the max FO plus FE is a max already. All right, that's what we call normal adjustment. So then, other than that, we have to pull it back. When pull back, it will be less. So it will be less than FO plus FE. So just now we have the three different results, right? When it's equal, that is for the max on the telescope. So max on the telescope, we call it normal adjustment. Okay. Then the other one will be less. It's also for telescope. Right? This is also for telescope. So it means our left only one, this is more than that, more than FO plus FE, this is only for the microscope. Right? This is for the microscope. So when the essay questions given ask you to choose the adjustments, arrangements for the lenses between the length between the lenses, so it will give you either equal, greater, or less. So you have to know whether there is an application for the telescope, application for the microscope. So once for the microscope, there is only one possibility, must be more. It cannot be equal, cannot be less. This is the first thing, how we knowing about the adjustment for the lenses. Okay. So now the first thing, the length between the lenses for telescope and microscope, how we arrange it is okay? Yes, please raise your hand. All right. So once you understand from the concept itself, okay, it will be easier for you to recall back. Okay, compared to you just study and try to memorize all the statements given, right? Actually, it will be more difficult. Okay, it will be more easier if you understand the concept about the design. Okay, so this is the one. Okay, so the next one is about the FO versus FE. Which one it should be longer? Which one should be shorter? Because application in the telescope and microscope difference, right? It must be one bigger, one longer F, one shorter F. But which one is applied on microscope? Which one applied on the telescope? Okay. So back to the design itself. Okay, here. This is a telescope, objective lens, the telescope eyepiece lens here. Okay, so actually eyepiece lens here, Okay, so here is this is prism. Sorry, it's a prism deflect the light to change the angle. Right. So okay, usually our eyepiece lens is inside here before the prism. Okay. So anyway, here is the objective lens and the eyepiece lens. So this is the one eyepiece lens for the microscope and the objective lens for the microscope. Okay. So now I want to ask you. Okay. Which one easily for you to recall back the size of the objective lens and the eyepiece lens have a significance difference. Which one? The size of the objective lens compared to the size of the eyepiece lens have a significance difference. It's easier for you to recall back. Which one? Obviously, there's a bigger, obviously, there's a smaller, comparing objective lens and eyepiece lens. Please respond my questions. The size of the lenses. Right? Okay, thank you for the engineering to respond. Okay, so telescope is the one that easier for us to recall back. Okay, the size is obviously different between the objective lens and eyepiece lens. Microscope, you see the design itself, microscope, okay, it's almost the same. The size almost the same. So, but the telescope, we can see obviously one will be bigger, one will be smaller. Okay, so same as the diagram that I draw before this. We're talking about the telescope. So you're getting smaller and smaller. Right, so this is a telescope. We have the objective lens, and then we have the eyepiece lens here. So from here, objective lens, eyepiece lens. Right, eyepiece lens here. So when objective lens is bigger means that according to the curvature of the lenses, center, right, diameter here, this is a center, right? So we're talking about this curvature. So our focus will be half of the radius. So focus length will be half of the radius. So when you have the bigger size of the objective lens means that your FO will be bigger. So obviously this is a bigger means that our FO, FE, so FO will be more than FE. FO will be more than FE. So for these two verses, okay, FO more than FE will be reserved for the telescope. Okay, and the FO less than FE will be for microscope. Right, compound microscope. Okay, it's just remember either one. Right, so normally I would ask the student focus on the telescope, because telescope, you know that it can be adjust the lenses, the length between the lenses. When you put until the max, that one will be we call it normal adjustment, which is the length is equal, the length between the lenses is equal to the FO plus FE. Okay, when you pull back, it will be less lah. So this is the first about the length between the lenses. Second, the telescope, you can recall back easily. The objective lens is much bigger compared to eyepiece lens. When you have the bigger size of the objective lens, so we have the bigger FO. FE will be shorter. So FO more than FE for the telescope. And then the other ones, FO less than FE will be for microscope. Okay, so once these two settle, then will be easier, right? Will be easier for the rest already. Okay, because usually when the essay question asks, first one of the characteristics, it will ask about the length between the lenses, the adjustment about the lenses. Okay, so that one compared to the FO plus FE. Second, it will ask about the FO and FE, which one big, which one longer, which one shorter. Right? So when we look at the size of the lens, so bigger size, it will have a longer focus length. Okay, so that's why we know FO is more than FE for telescope. Okay, so once we settle about these two important concepts, then the next one we can focus on the drawing already, about how the image is formed. Okay, first we need to have two lenses. Now we focus on the telescope. We focus on telescope. Okay, telescope for the. Okay, we focus on the telescope. On the normal adjustment, which is length equal to the FO plus FE. And remember, telescope, FO more than FE. Right. So remember about these two. Okay, why is so important? Because when it's equal, means that FO and FE shading on the same point between the lenses. So shading on the same point, you cannot just put at the center. You cannot, because when you put on the center, it means that this one is an objective lens, this one is an eyepiece lens. When you put at the center, it means that here, if your FO, and here, if your FE. So it's showing that length is equal, FO plus FE is correct, but it's wrong for the second term and condition, because you have to show FO is more than FE. So when you show in the center, then it's wrong. So how to do? FO more than FE. So it means that objective length must have a longer. Okay, objective length must have a longer F. Okay. So it means slightly backward here. Example. So here will be this one will be the FO, and also it's a FE. So now FE shorter, FO longer. So like this. All right. So this one settled. Okay. So now how are we going to form the image? Okay. For the telescope, we use to observe very far away objects. Okay. Telescope we use to observe very far away objects. So it means that we can imagine the object located at infinity. So it means that we can't show where is our object in the light game, because object is far away. So when you cannot show the object positions, okay, hold on. Okay, so we cannot show the object position, object far away. So when object far away, we have to show there is a two parallel ray. One must pass through the optic center. Still remember what we learned the drawing yesterday. So when you have the lens here, so eyepiece lens we're talking later. So once of the light ray must automatically pass to the optic center. Okay. But the problem is we do have the object. So where to pass optic center? So we just draw any one ray, pass to the objects. Okay. Pass to this optic center and then go straight. Okay. So and then next one is what? Next one must be another parallel ray. Next one must be another parallel ray, which is must go to the F first. We cannot draw the second line that we learned yesterday, which is parallel with the principal axis. We cannot draw this one parallel with the principal axis. We cannot draw this. And after that, go to the F. We cannot, because we don't have the objects shown in our diagram. Then what to do? We must get the one parallel ray, pass to the focus point first. Pass to focus point first, and after that, continue lead into the position of the lens. Right? So this focus point must be the same of the FO that show in your light game. So you must know where is the correct positions for this same FO. So we wait from the other side here. So the FO will be here, this one. This is our FO here, okay? So it means that the FO should be here, somewhere here, okay? So then we get another parallel ray. So use your ruler, get another parallel ray, okay, with this one, and pass to the F here like this. Okay, so this is our parallel ray. Okay, then after from here, we continue parallel with the principal axis. So we draw parallel with the principal axis. Okay, parallel with the principal axis. Then we stop right before the eyepiece lens. Okay, so this is our. So here we forming the image here. And anyway, one of the guidelines for you is the image, the first image formed by the objective lens, it will be formed right on the focus point. It will be formed right on the focus point. Okay, just like the ligand that you learned before for the first ligand. This one. When object is from the infinity, so image will be located at F. And it will be the real, inverted, and diminished. Why we able to know diminish when the object is located far away? Okay, because when the object located far away, we still can see the image formed by the lens. For sure, the object is very big. Can you imagine that a small fly, okay, 1,000 kilometers away, can you use the telescope to see that small fly? Definitely cannot. You only can use it to observe the object far away, but the object is big. For example, we can use it to observe something like planets or what, okay, or the aeroplane on the sky, which is original the size of it is very big. Okay, but because it's very big, when far away, it's still able to be captured by using the our lens instruments, optical instruments, right? So that's why no matter how, the image form will be diminished, right? Okay, so this is the one. Okay, this is the first image. So it will be real. It must be real. Either microscope or telescope. Your first image must be real. Because if you know the first image is not the real, then you cannot use it as an object for the eyepiece lens. Because the first image, it will be functions as an object for the eyepiece lens. Remember, the first image formed by the objective lens, it will be function as an object for the eyepiece lens. All right. So now our first image form done already. This is first image form. Now we're going to focus on our eyepiece lens, which is a second lens. All right. So in this case, okay, we're still doing the drawing like we learned before this. Now we have the objects. We have the objects already. Actually, it's the image, first image. We make it as an object for the eyepiece lens. So now from here, we parallel towards the position of the lens. And then after that, you have to go to the focus right. So now we need to know where is the focus FE. So we get the same distance behind here, so FE. Then we go through FE. So go through FE. All right. So this is how the light travel. Okay. And remember yesterday I told you the next one it should be go to the always have the one go to optic center. So this one go to optic center. Okay. So what happened is you notice that this one will be parallel ray. So it means that the image actually the image cannot be formed. Final image cannot be formed. Okay, final image cannot be formed. All right. So we only get the parallel ray enter into the eyes. So what happened to this light ray, which is from this yellow one? We go straight forward here until this. So what happened to these ones? This one. Okay, so we just need to draw another. Okay, same parallel with the other ray. Just like this. We don't need to care whether you go to F or go to optic center. No, we just make it draw parallel. So all parallelly enter the eyes. So this is what happens on the normal adjustment telescope. This is what happens. All right. So, and then the final image, how? Okay. So is it we can say that there will be no image can be seen by the eyes. Actually, it's not. You have to remember, our eyeball also a lens. Our eyeball also is a lens, right? So once we have the parallel ray enter our lens, just like this one, we have the parallel ray enter the lens, just like our eyes. So actually, it will forming the sharp image on our retina, right? So when you have the parallel ray enter our eyes, actually it will able to forming the sharp image on our retina, and this sharp image, okay, will be exactly just like our objective lens forming the image. Now only the difference is this one, it will be forming what? We will forming the image, final image is like this. Because of what? We have the object is upside down. We have the first image as object upside down. This one, object far away, upright here, far away, and then forming image is inverted. And this inverted, after go through eye lens as a parallel ray enter the eyes, final image will be upright again. Okay, final image will be upright. Okay, so this is what happened. So if you how to say that? Okay, so okay, maybe we use the other ones for the shorter. This one's a normal adjustment. We can't see the image, final image in our right game, right? But if we use a shorter, which is less than the max, we pull it back. Once we pull it back, then you will see what happens. So now we're going to less than normal adjustment. Less than normal adjustment means that we're going to have the length between the lenses is less than FO plus FE. So less than FO plus FE, so it will overlapping. So let's say I use the yellow colors as our objective lens. So now I have the FO is longer, FOO is longer. So this is our FO. So on the other side also have the FO. All right, okay. And I use a blue color as FE. So actually it's better I make it closer. So let's say this is FE. Okay, so now same as just now. Okay, we have the one ray. First image must all located on the focus point, so you can reverse the drawing. Okay, if you already can get, if you have the ruler, it's better lah. Right, so I don't have the ruler, so I have to reverse the drawing to make sure that it's the FO is correct here. Right, so these two is parallel ray. Right, pass to optic center and the parallel with the principal focus. When it go to F, parallel with the principal focus. So this is my first image. Right, so I label FO here. So this is my first image forming on the FO. Right, first image forming on the FO here. Right, and then the first image will be acting as a as object for the eyepiece lens. Okay, so now in this case here, so you see, we're going to continue this for the objects, which is the first image as the object, parallel with the principal focus, and after that go through the focus point here, and then we have to extend it. Okay, this is the first one, and the next one you go to the optic center, right? Optic center. So when I extend it, so the image will be formed. Okay, very far away lah. Okay, so I can't okay because I using the f a bit longer, right? So that's why you make the image far away. But obviously you see that the image will be formed somewhere beyond here on the left hand side. So because it's getting closer and closer, it will form the sharp image. Okay, so image will be final image will be the okay upright. Okay, why we say final image upright? Because we comparing to the first image. But when we comparing to the object, it's still inverted. Right? When comparing to the object, it's still inverted. But this one is a virtual image. Because of what? Our light is deflected after the lens, but the image formed before the lens. Means the image form same part as our first image. So image forming here, this one the image actually is a virtual image because it's not forming after the lens, after the eyepiece lens. It's forming before the eyepiece lens, so it's a virtual image. But this virtual image, okay, is not inverted. This virtual image is upright. Why we say this virtual image is upright? Because we comparing with the first image. Second image compared to the first image is considered as an upright. Okay, upright, virtual, and magnified. So by right, virtual, okay, by right, virtual is always upright, right? Okay, so this is what we get upright. But the problem is when you're talking about this final image compared to our objects, which is far away. So this final virtual image is, we call it inverted when we give the answer, because we don't compare the final image with the first image, which is acting as an object for the eyepiece lens. We still comment the final image characteristic with our original object, not the first image acting as an object for eyepiece lens. We still compare to our original first-hand object from the eyes from the objective lens. So this one is a virtual image, but it's inverted. That's why the virtual plus upright padding is not applied here. Virtual plus upright padding is only applied for the single lens. But once on the optical instrument, it's not applied. Okay, because of that. All right. So when you look at the textbook, okay, for the telescope, you see the final image I2, virtual, magnified, inverted. Compared to what? Compared to object. Right? So this is something that you must know. Virtual, magnified, inverted. Okay, compared to the object. So now, as I repeat again, virtual upright padding is not applied here. Virtual plus upright padding is only for single lens. Okay, but once applied in the optical instrument, which is combines of the lenses, we have the second image as the final image. So this second image, final image compared to object, so it becomes virtual, magnified, inverted. All right, okay. So okay, and then this is for the telescope. Okay, so but why usually when we do the adjustment, we always go to normal adjustment. We use a normal adjustment because of what? Even the normal adjustment, our image form at the infinity. Okay, but this infinity actually will make our eyes comfortable in our vision. Okay, because we no need to specific focus on the final image form. Because the final image is parallel, then we let the light parallelly enter to our eyes, so it will have a sharp image forming on the retina. So it will make us comfortable to see the final image. Okay, but it's a final image forming virtually on the fixed positions. So our eyes have to be focused. Somehow our retina have to adjust, okay, so that we can focus on that image, final image forming on that position. So, but because most of the time it will be far away, okay, as you from the diagram you see here. So that's why usually we will go through normal adjustment, right? So that we can have the comfortable vision. Okay. So this is about the telescope. Okay, and we have the one magnification calculations. This one I'm not sure whether exam will ask or not, because usually we will teach, but we seldom have the question for this. Okay, which is a magnification for the telescope when it's not at normal adjustment, only apply a normal adjustment. So this magnification will be FO over FE. Okay, so remember, because our final image is the magnified image, so that's why and then we know that telescope we have the FO more than FE. So that's why when you want to calculate the magnification, we will use the FO over FE. So it's not like the magnification that you learned before. We always use the image over the object. No, this one we use the FO over FE. No, it's nothing to do with the object distance, image distance. It's talking about the focus length. All right. So since that we know the FO is more than FE, so that's why we use FO over FE for the magnifications of the telescope at the normal adjustment only apply. All right, FO over FE. So that when the time we want to buy the telescope, we want to build the telescope, so we want to know that how big can be amplify the final image. So we look at the ratio of the FO to FE. So this is how we're going to choose the lenses. How much of the FO and FE comparing the ratio between the objective lens and the eyepiece lens. Right. So if the ratio is really really small, then the magnification will be small. The ratio is big, FO over FE, the ratio is big, then you can have the bigger magnifications. All right. So now the next one is for the microscope. Okay. For the microscope, once you understand the telescope already, microscope is quite easier. Right. Only have the one special term and condition for microscope. First one for microscope, you have to recall what I told you just now. For the microscope, which is the length, it must be more than FO plus FE. Okay, more than FO plus FE, means that the length between the lenses should be far away, because it must be more than FO plus FE. So the next one, FO is less than FE, because FO more than FE is for the telescope, bigger lens towards smaller lens. So the microscope will be reversed. So it will have a shorter FO compared to shorter FE. But this smaller FO, bigger FE is not significant difference. It's just only slightly small, right? For the design of the microscope inside, you can see the lens size actually almost same, because both is a high power lens. High power lens means you have a smaller f, right? So that's why both lens is small, right? Okay. So anyway, we need to show here. Okay, so we have the two lenses here. Just like just now, I use these yellow colors as an objective lens. Okay, and after that, I use a blue color for the eyepiece lens. Okay, so now, okay, so let's say I have the FO here. So on the other side, also have the FO. Okay, and then we have the FE here. FE will be slightly more than FO, so I make it slightly more. So FE. So the drawing is very similar with the telescope. All right, drawing is very similar to the telescope. Okay. So now it must have the gap in between, because the length between the lenses is more than total FO plus FE. So that's why FO FE in between have the gap. Okay. So now it's done already. So only one thing different is telescope object far away, but microscope we have the specific object distance. Okay, so this specific object distance is, it must be between f and 2f. Sorry, object distance must be between f and 2f, because when your object located less than f, it will form virtual image. So the first image is virtual, then you cannot form the final image already. So the first image must be there. When the first image must be there, it means it must be more than f. This is the first thing. Second thing is, we need to magnify the final image. So to magnify the final image, we need help from the objective lens, so that the first image is already magnified. Then the first image magnified as an object for the eyepiece lens, so our final image will be magnified even bigger. So to magnify the first image, we only choice is objects must located between 2f and f. Because once object located equal to 2f, our image form will be same size. Back to the concept that we learned before, the drawing. Or when object located beyond the 2f, our first image will be smaller. So that's why to make the first image bigger, we must locate it between 2f and f. Right. So our object must be here. So let's say this is our object. Okay. So between f and 2f. So now we apply the drawing as what we learned before. First, must always go through the optic center, which is here, object center here. Then we go straight. Right, you go straight until before the second lens, eyepiece lens position. So I extend this eyepiece lens position here. Okay, so like this. Okay, this is the first ray. Second ray, for the object, we parallel with the principal focus, and afterward we go to the focus point. From here we go to focus point. Okay, so we form. Okay, we form our first image. Okay, so I make smaller a bit. All right. Okay, so like this. So I adjust a bit for our FO, so that easier for you to understand how it look like. Okay, so I adjust a bit. Okay. Then our FO is here. Okay. FO. All right. So okay. Then our first image. First image forming here. This is our first image. Okay, first image forming here. So this first image, it will be acting as an object for eyepiece lens. First image, I1. Okay, so from here we continue our drawing. So from here, and we go through the optic center here. We go through optic center. I smallest bits that I get. Go through optic center. Okay, second, from here parallel with the principal axis, and after that go through the focus point, and we extend it. So this is our final image is here. Okay, so the rest here you can continue this one. Just now I said that this one how to continue. We don't need to go to F. We are not going to optic center. So what we need to do is we adjust the anchor until it meet on the same point like this. Okay, we adjust the anchor so that it can meet the same point. If you want to draw, if you don't draw, it's just leave it. It's just leave it. Okay, and then this one here, I have to erase it. Okay. So for this one, you want to continue from here also can. Also go to the same point, and then you adjust the anchor, and then it will be like this. So if you don't want to draw, it's fine. So they all meet on the same point, focus on the same point. So this is our final image, I2. This is our final image, I2. Okay. Here is a final image. Okay, so this is the first image. This is our objects. Here is object. This is final image I2. And this is the first image I1. Okay. So same as just now, when we comment the characteristic of the final image, right, we have to compare to our objects. So this final image is virtual, right, because it's forming before the eyepiece lens. So it's not forming after the eyepiece lens. That's why this image we call it virtual image. Okay, and this virtual image compared to the objects is inverted. So again, virtual upright, this padding is not applied here because this one is a virtual inverted. Due to this one is a second image form, right? So we compare to the object, so it's a virtual inverted and magnified. So when you go to the back, go to books here, you see the final image, virtual, magnified, inverted, compared to object, right? So basically, first image, second image, either telescope or microscope, exactly characteristic exactly the same. Exactly the same, the result compared to the object. Only the difference is the arrangement of the lenses and the position of the objects. Microscope, we see the object located between f and 2f of the eyepiece of the objective lens. But the telescope, we use to observe the object far away at infinitive. But because of the arrangement of the lens, FO and FE bigger, shorter, and the length between the lenses, that's why it will be able to form the final magnified virtual inverted image. Both are the same. That is why when the student read, they're confusing, right? Because the result actually is the same. Either the first image or either the final image. But because of arrangement difference, to make the this differing to the different objects, so that's why, okay, arrangement will be different. So this is how to understand about the microscope. Okay, so this example, as I show this one. So in the textbook, it show obviously different between FO and FE. So you can do so. Only the concept is, remember, okay, FO, FE, FO is shorter for microscope, right? But the microscope, actually, we don't really have the obviously difference between F1 and FE because both actually is a high power lens. But in this ligand, okay, somehow it's showing obviously different size. Okay, for me, it's not really good to show you that because you see the real applications, right? So we don't really have much significance difference lah, right? Okay, so depends on the powers, depends on the power. But anyway, we don't have the magnification calculation for the microscope in this moment, right? For the SPN level, we only told you about the magnification for the telescope when it's for the normal adjustment. Okay, we don't apply in microscope, right? Okay, so somehow for this optical instrument, actually there are more concept you need to learn when you go to the specific field, right, in the university. And actually in university for the optical, only optical, okay, the concept about optics, actually there is a one topics. No, one topic is a one subjects. It's a one subjects in university. But for your SPN level, it's just only a subtopics, a small subtopics in your syllabus. So you can see that the knowledge that you learn actually is very, very shallow, right? So this is about the instruments, optical instruments. Okay, so there are some others of concept that we use in the our smartphone, our CCTV. So this one for you to read and get to know the technology that we apply. So actually we have no much focus on that. It's just only some statement you need to know. Example, the lens used to form the image that is a real, diminished, and inverted, okay, at the sensor. So when we use a sensor to process the final image appear on the screen, it will be back to upright. right? But the sensor actually detects is a inverted, okay, image, and then it's a real image. Must be real because it have to form the image on the sensor. It cannot be virtual image. This one is for sure. Okay. So that's all for these optical instruments, right? So far, is there any questions? It's okay to proceed the last part. Okay, please raise your hand. Okay, so anyway, for this optical instrument, you still need time to digest all the knowledge and to find a way to easily for yourself to recall back during the exam, because the content inside understanding about this optical instrument is quite a lot of the content. So I really try to make the conclusion easily for you to recall back. But if you think it's not suitable for you, you have to find your own way to easily recall back about this optical instruments knowledge. Okay, so now next one we go to the spherical mirrors, which is a curved mirror. We have the concave mirror and the convex mirror. Okay, so convex mirror and concave mirror still the same. Our main focus will be on the drawing to know about the characteristic of the image. That's why you still have another table similar like the lenses. Okay, for the convex and concave mirror. All right. So and as usual, I know you for my student, you shouldn't go and memorize. Okay, memorize all the different object distance to knowing about the characteristic of the image form, because you shouldn't do so. You must find a way to understand by the drawing or by calculations. This one also we can do the calculations to knowing about the characteristic of the image form. All right, so I'm going to show you that first before I go through the drawing. Okay, but before that, another one correction, same like our convex lens. Concave mirror also same. When the object equal to f, when the object at f, we cannot comment characteristic of the image. All right, so because what image form at infinity, so there's no such thing behind mirror, right? Because we don't know whether there's a real or virtual, right? So we only can comment image at infinity, right? But if really SPN question asks how, if the SPN question really asks, you have no choice, then you remove all the cover. So you follow this. If SPN asks, I have no choice, because it's always stated in textbook they have no official corrections for this. Okay, but somehow this is wrong. Okay, so what to do? Because SPM, we cannot expect the question is perfect, correct. Every year have errors, sorry to say so. Right? Even the latest SPN 2021. Right? So later I show you SPN 2021 what is the big errors, okay, in the questions. Right? For those have the books, you can get ready the SPN 2021, have a look for the questions. Okay, very shame to design the questions by the panel, showing that the somehow the question can solve, but the problem is the way of the design according to SPN level. It shouldn't design the question in the way. It seems like they are the wrong concept questions. Right? So later I told you. Okay. So anyway, highlight about this one. Okay, it's possible to cover it. It's wrong. Okay. So now, how are we going to apply calculations to knowing about the characteristic of the image formed by the concave or convex mirror? Okay, so here. Right, so we are finishing soon. Okay, because as long as the lens, you already mastery about the lenses. So for this mirror is quite very easy, right? For this mirror is very easy. Okay, so now, concave mirror concave mirror, you make it similar as a convex lens. Convex mirror, you make it similar as a concave lens. When we want to do the calculations by knowing the characteristic of the image, so you're assuming that is the way how they works. Drawing different, drawing totally different. But by the calculation, because calculation, we need to borrow the lens equations to knowing about the characteristic of the image formed by the mirror. So you have to assuming that this. Okay, so it means that when you see there's a concave mirror, when you apply the calculation for with the lens equation, you have to make it similar like the convex lens. So means that our F is the real F, real focus. So F is positive. But the convex mirror, because it's just acting like the concave lens in our calculation, so F will be the virtual F. So it means that F is negative. F will be negative. So first. Second, when the V is positive, for the both lah, okay, for the both, sorry. For the both calculation, when the V positive, so it's still the same, it's a real V. When the real must be inverted. Okay. If the V is negative, so means it's a virtual V. Virtual V means must be upright. So it still will be the same as what we applied before this. Okay, so now you see. So let's say I take anyone's like games here. So let's say we don't want to focus on the drawing. We focus on the term and condition here. So let's say we're talking about this C object beyond the C. Okay, what is a C here? Okay, C actually equal to 2F. Later I explain what's a C. Okay, so C actually is a 2F. Okay, so it means that when the object beyond the C, so object is more than 2F. So in the case here, this one is the concave mirror. Concave mirror. Concave mirror, we make it similar as a convex lens. Convex lens means that the F is positive. Okay, so we try to make, let's say F is 10 centimeter. Let's say we make the F as 10 centimeters. So the U in this case should be more than 2F. So we make the U more than 2F. So let's say we make the U as a 25. So consider as more than 2F. Okay, 25. So now we do the calculations. 1 over 10 plus 1 over 25. No plus. Sorry. 1 over 10 equal to 1 over 25 plus 1 over V. So 1 over V will equal to 1 over 10 minus 1 over 25. So use your calculator. Why I get 25? Difficult for me to count. Can I change? I change to 30 lah. Easy for me to count. I change to 30 lah. All right. I change to 30. Easy for me to do a calculation manually. All right. So it means that we have the 3 minus 1 over 30. Right. So it means I have the 2 over 30. Right, so it's equal to 1 over 15. So it means that our V is equal to 15. V equal to 15. So in this case, we get the V is positive V. So positive means it's a real. Real must be inverted. Okay, and then the 15 compared to the object distance, 30. So V is smaller. All right, so diminish. Right, so that's why we know. And when you look at the result here, so real, inverted, diminish. Right, real, inverted, diminish. So there's a result, right, by calculation. So you can try to apply the rest. Okay, so you will know the result. Okay, this is based on the calculations. So you can apply same for this concave mirror. Concave mirror, it will be acting like the convex mirror. Sorry, convex mirror, it will acting like a concave lens. So it means that when you do the calculations, f should be negative, right? F should be negative. So when you do the calculation, you will knowing about all the characteristics of the image. So this is about the way how we calculate by borrow the lens equations, apply in the mirror to knowing about the characteristics of the image formed by the curved mirror or the spherical mirror. Is this okay for you? If yes, please raise your hand. All right. So mostly it's okay, huh? Okay, so the next one is about the drawing. So drawing, how to understand comparing to the lenses, the difference with the lenses. Okay. So now I use a two example. So this is a lens, right? And then for the mirror, so let's say I have the concave mirror. Okay, concave mirror. So here's our objects. Here's objects. Okay. So for the lens, okay, we have the optic center. Optic center, which is the center here. Optic center. Okay. But for the mirror, we have the center of curvature, which is the curvature of the mirror. So this curvature is a part of the circle. It's a part of the circle. The part of the circle. So then we have the one thing we call center of the curvature, which is the center of the circle. Just like in the textbook given here. Okay, so this one. So the spherical mirror, actually the curvatures of the mirror is a part of the circle, right? It's a spherical. So and then according to this, we will have the center here. This is the center of the curvature. Center of the curvature, all right, C. And then from the C towards the surface of the mirror here, this is the radius. This is the radius, right? So half of the radius, it will be the focus point located. Half of the radius will be the center of the, or will be the focus point located. So it means that this length, half of the radius actually is a focus length. So the other half of the radius here, this is also half of the radius. So that's why the C also considered as a second, the 2F. Because when let's say the F is 5 centimeter, so here for 5 centimeter, here's another 5 centimeter, so become C as a 2F. But we don't call it as a 2F. We only call 2F for the lens. But this one, the 2F actually is acting as a center of the curvature. Center of curvature, all right? Just like the explanation given here. Center of the curvature, right? Okay, it's a center of the sphere which is produce a concave or the convex mirror. Okay, so the radius, as I explained to you just now, so you can read through, okay, for understand what I show you by the right game. Okay, so that's why, okay, so here, okay, for the drawing itself, you see, I already teach you before, when you have the objects, so from the top of the object, straight away go to the optic center, go straight line. So we're only going to apply the same thing for the mirror, okay? Once you see that it's an object, then you know where is the center of curvature. So the first thing, from the object toward the center of curvature, go straight line, no matter how, go straight line straight away. Okay, so to make it easier for you to see the whole part of the ligand, so I adjust a bit for the center of the curvature. I make it shorter a bit for you, okay? So that you can see. So let's say here, This is my center of the curvature. Then the half here will be the focus line. Okay, focus point. Okay, so first line, what we learned before, from the object toward the optic center. So go straight. Okay, and then we apply the same thing for our lens, our mirror. From the object toward the center of curvature, go straight until the positions where is a mirror. Then we stop here. So this is always the same. Okay, and then the second. Okay, so what we're going to do for the second is, second will be parallel with the principal axis, right? Parallel with the principal axis, and after we'll go to focus point. So I'll show the focus point here. Focus point. Okay. So from here, parallel with the principal axis, and after that, go to the focus point. Then we form the image. Okay, so extend this one. So we form the image. Okay. I extend a bit. Okay, so the image is formed here. So now we form the image already. Okay. So this is real image. Okay. But for the mirror, how? Okay, same. For the mirror, still same. After we go through the C straight line, which is the first ray we draw. Second ray, from the object, parallel with the principal axis, horizontally, go through the mirror. And after that, we go to the F. Where is the F? Remember, F itself must be inside the sphere, inside the circle of the curvature, right? So that's why the F must be here, okay? Because our curvature, part of the curvature is like this. The part of the curvature according to the mirror that we have. So inside the circle, so that's why it's inside here, right? So we reflect towards the F. So it's like this, okay? So it's like this. Okay, remember, for the mirror is deflections. Light hit the mirror, deflect. So remember, the light hit the mirror, deflect. Hit the mirror, deflect. This one also incident ray, deflected back, deflect. So all the deflected ray, they meet, so they form the image. This is image form here. So we're forming the image here. Image form here. Okay. So this one we call it real image. Because of what? Okay. Because the light deflected and meets. So it's based on the deflected ray. So when you put the screen here, it's the light hit on the screen, projected on the screen. So that's why it's just a real image. But for the lens, this one, the lens, because the lens is based on the diffractions. So the light is penetrate throughout the lens. Enter and out. So diffracted. And then this one is real. So if you're talking about the positions, you're talking about position, right? So the image for the lens, image forming by the lens is not same side as the object, we call it real. But for the mirror, when the image form same side as the object, we call it real. So when the student learning about talking about the same side or not, right? The student actually confusing. But if you understand based on the phenomena of the light, okay, for the mirror is deflect, okay, hit and deflect. So that's why when you forming in front the mirror, they want we call it real image. But somehow the characteristics still the same. When it's real, real always inverted. Real always inverted. Remember, real always inverted. Real always inverted. Okay? So that is the way how we apply the drawing. Okay. So with the true ray like this, enough already. Okay. So what happened if we forming the virtual image? We forming the virtual image. Okay. So now we're talking about the mirrors. We focus on mirror. Okay, so here is this is our concave mirror. So let's say here is my F. So I have the object located here. This object less than F. So the drawing, first one, Okay, sorry, I have to make it smaller a bit because we need center of curvature. So that's why here is a F, and then the others, okay, 2F. Actually, it's a 2F, right? Center of curvature. So when you have the object is here, okay. So the first thing, from the object toward the center of curvature, always straight line. The first thing going to draw, this one. From here to the object, to the center of curvature. Then go straight line until you meet the mirror. Okay, so like this. This is the first. Okay. Second, parallel from the object, parallel to the principal focus. And when you hit the mirror, it will be reflect towards the focus point. Towards the focus point. Okay, and then you extend it. You extend it. Okay. So here, this one you're going to extend it so that they will meet. Then your image, final image forming here. So that is your image. Okay. Here is your image. But when we show the arrow, okay, incident ray on this center of curvature and they hit the mirror, deflected back. Right. For this parallel towards the mirror, and then deflected towards the focus. So means that whatever after the mirror, it will be virtual. Whatever after the mirror actually is a virtual. Okay, actually it's a virtual. Because the light is deflected back by the mirror. So whatever forming after the mirror actually is a virtual. It cannot be projected on the screen. It's a virtual image. Right? So here, when we know that it's a virtual, you see the virtual always upright. Virtual always upright. And then the size is just compared, then you know. Okay, the size will be really fine. So this is for the concave mirror. When apply on the convex mirror, how we draw? Convex mirror. Okay, so this is convex mirror. Convex mirror, right? Convex mirror, and objects located here. Object located here. Okay, object located here. So we have a convex mirror. For the convex mirror, when we complete the circle, it's behind here. So it means that our C and F will be behind the mirror. So here is the F, here will be the C. It will be behind the mirror, not like the concave. Concave, it will be in front of the mirror. It means that on the object side, which call it in front of the mirror on the object side. Okay, but this one I call it behind the mirror because it's not on the object side. Object always stand right in front of the mirror. So, but the F and the C, it will be behind the mirror. Okay, so because we follow curvature. Okay, and then drawing is still the same. So drawing is still the same. From the object, you see object, and then you know the C. So straight line from object towards the C. Object towards the C, straight line. Okay, object towards the C. But when you hit the mirror, it will deflect back. So it means that whatever behind the mirrors here, it will be the virtual. Okay, as I mentioned earlier before, you want to use it dotted lines or not, it's up to you. Doesn't matter, right? So this one will be virtual because when you hit the mirror, it will deflect back. But anyway, this line, it will be referring to the C, straight line. Okay, straight line referring to the C. Okay, and then the second line, still the same as just now, parallel with the principal axis. Parallel with principal axis toward the mirror. So here you are, parallel with principal axis toward the mirror. And afterward, we deferring to the F. It will be deflected from the F. Deflected from the F. So we're deflected from the F. Deflected. So it will be like this. So it will be deflected. Hit the mirror, deflect. And then after that, behind the mirror, it will be the dotted line. So where they meet here. So the deflected ray, they meet, forming the image. So the image forming here. So here you are, the image. Okay, here is your image. There is your image. All right. Okay, so the image will be virtual. Okay, virtual, upright, and diminish. So this is the drawing. Once you understand the concept drawing on the lens, it will be easier for you to master the drawing on the spherical mirror. Only the difference is spherical mirror, you need to know where is your F and where is your C. So after that, the drawing of the ray is still the same. Okay, so this is how we forming the image by the drawing ray like that. All this actually is already shown in the textbook. Just to let you know the concept on this drawing, not just by the memorize. Okay, so hopefully you can master the drawing method, because the drawing method is very useful for you to understand the image, okay, better. Okay, and then the next one is the applications of the concave and the convex mirror in our daily life. Basically, usually we always use a convex mirror, lah. All right. So because a convex mirror is convex mirror, usually we will use the convex mirror, okay, because the convex mirror, it will give the wider range of view. Okay, like this one, you see. Where is it? Here. Okay, convex mirror, it will give the wider range of view. Okay, but for concave mirror, it will be narrow down the vision. Okay, narrow down the vision. But the concave mirror advantage is what? You have the possibility to magnify the image. Right? You have the chance to magnify the image. Okay. No magnify the objects, magnify the image, remember. But for the convex mirror, image always diminish. But the advantage is what? It can widen the view. So that's why for this blind spot mirror, we use a convex mirror. We use a convex mirror because it can widen the view, so that we can see the blind spot. All right. So so the lantern is using to magnify the image. So it means that the lantern actually using the concave mirror. They are not using the plane mirror, because the plane mirror, it cannot be magnified. It cannot be magnified the image. Plane mirror always same size. So that's why sometimes I heard that the ladies in the shopping center, they will comment, I don't like to use the mirror in the shopping center. When I changing the clothes, when I stand in front of the mirror, always looks bigger. I always do myself bigger. Okay. So if there is a plane mirror supply provided, it should be same size. It's not bigger. You do bigger because your self original is bigger. That's why I do bigger. Right. But right there is only the plane mirror. It's the same size. Only the curved mirror, it will be change the size of the image that view. All right. So I don't know. Maybe some store, they should use that. Maybe they have to use a convex or concave, so that when you stand right in front, it will look smaller. So it depends. Okay. So yeah. So there's an example. We use the convex mirror in our daily life. So bright spot, the security mirror, right? So the vehicle, the rear mirror, so that we can get wider the view. Right? So that's why I said that usually in our daily life, we apply convex mirror. Okay, only in the certain case we apply concave mirror, so that we can magnify the image. Okay, so but once you use a concave mirror, it will be wider. It will be smaller. It will narrow down the angle of the view, right? So for the cosmetic mirror also same, they're going to magnify, the image, so that you can zoom in and easily when we want to make up. All right. So I think that's all for this chapter 6. All right. Okay. So hopefully you already learned how to study for this chapter 6, which is chapter 5 and 6. Actually, the most of students having a problem for these two chapters. I don't know why. I think maybe because there's a lot, the content is much more, because they have the drawing, they have the calculation, and then there's the application concept and so on. So anyway, I try to give you more example questions into the Google Classroom soon. So hopefully that it can be help you to improve your understanding. Okay, I think that's all for today. Thank you for joining the class for this 2 days. All right, even this only 40 plus of you. Okay, so I think that's all. Okay, thanks. If you have any question, you can ask. If not, you can left now. Thank you.